Good day, I'm Dr. T. Welcome to my office. This is the April 4th, 2020 Q&A. So two questions are from the class discussion boards. First question, difference between cis and trans fatty acids. So some context. Fatty acids are going to be a whole bunch of carbons, and on one end is going to be an acid functional group. Now, for the rest of those carbons, that could just be a straight alkane. So just CH2, CH2, CH2 until the very end, which is a CH3. In that case, we call those saturated fatty acids. You can't add any more hydrogens onto them. Unsaturated fatty acids have one or more elements of unsaturation, which in this case means alkene, so a double bond. Monounsaturated, one alkene. Polyunsaturated, multiple alkenes. Fairly straightforward. Now, if you remember back to alkenes, they come in two flavors, cis or trans. If the carbons that make up the chain are on the same side of the double bond, because remember, double bonds don't rotate unlike singles, then that's a cis double bond. Now it's going to create a kink in the chain, which is why for unsaturated fatty acids, the cis variety, those are going to have higher melting points. Sorry, lower melting points, wrong way. You're going to have lower melting points because they don't pack as nicely as saturated fatty acids, which have these nice, very straight linear chains. Now, you can also have a trans double bond. And trans double bonds are going to be where the carbons are on opposite sides of the double bond. And in that case, it actually packs a lot better. It creates a squiggle instead of a bend or a kink. So trans fats will be solids at higher temperatures. Also, most biological systems are only used to cis fatty acids, so the trans fatty acids tend to cause some problems because they get incorporated in spots where they shouldn't be. Okay, the next question involved hydrolysis versus denaturation. So if you recall, proteins have four levels of structure. Quaternary and tertiary structure, which is held together by intermolecular forces between the R groups. Secondary structure, which is the hydrogen bonding between amide bonds, or the peptide bonds. And then there's primary structure, which is the actual covalent linking of the amino acids together via a peptide bond or an amide bond, depending on how you want to phrase it. It's the same thing. Denaturation, you are disrupting the intermolecular forces that are holding together these quaternary, tertiary, and secondary structures. So everything we would normally think of as intermolecular forces. You're not breaking covalent bonds, at least not typically. You might be breaking some for the disulfide bridges. In that case, reducing agents can be denaturing because it'll break those. We still call that denaturing. What you are not doing in denaturation is breaking those peptide bonds. If the peptide bonds are broken, that's a process called hydrolysis. So in this case, water is used to react with the amide that is the peptide bond, and that converts the amide into an acid and an amine. Well, at this point, there's no more a bond there. They're broken apart. So you're actually degrading the primary structure with hydrolysis. Hence the major difference. Effectively, your enzyme is going to be, or your protein is going to be pretty much toast no matter which one you do. But if you're denaturing it, it's still going to be attached together. It's kind of a glob of protein. It's probably not going to be in the right order to do anything particularly useful. Where if you hydrolyze it, it's going to be just straight amino acids. Typically, when you eat something, your body is going to start by denaturing it with acid in your stomach and then hydrolyzing it progressively to the point where it's amino acids, and that's what you absorb. So those were the two questions. So with that said, have a wonderful day.